going to talk about linear systems and how we solve linear systems. This should be, I think this should be view here, although it's working out that it doesn't, this is not, or this is not as you're not as comfortable with this as I would have thought you would have been, which is fine. That's okay. I mean, if you're not real familiar with this stuff, that's okay. Now you will be after we go through this unit. Solving linear systems. We're going to start off learning how to solve linear systems algebraically. There are two techniques for that, substitution and elimination. Those words might be familiar to you. Today we're going to talk about substitution and then how we would apply that. Okay, so first of all, though, before we jump into that, we want to remind ourselves what it means to be a solution to anything in math. In this case, we'll take the example of an equation. To be a solution of an equation, the variable or variables that we solve for, the values we get for those, in this case, two variables, because we have x's and y's in our equation. So this ordered pair, which is an x and a y value, would be a solution if it did what? How would we know whether the green ordered pair is a solution of the purple equation? Okay, if we plugged it in and it worked, it made the equation true, right? And we could easily plug that in and see if I plug 3 in for x and 6 in for y, do I get 24? 6 plus 18? I do. Yeah, I do. So yes, that one checks. What if I plug in 6 for x and 4 for y? Do I get 24? I do. Yes, I do. Check. So that is also a solution of this line. If I graph the line, what does the graph of an ordered pair look like in the xy plane? Like if I graph the ordered pair 3, 6, what am I graphing? A point, exactly. Okay, an ordered pair is a point. So because the green ordered pair and the red ordered pair were solutions of the purple equation, where would those points show up relative to the purple line if I graph the purple line? They have to be on the line, right? If an ordered pair is a solution of a linear equation, then it must correspond to a point on that line. And sure enough, if I graph the purple line and I graph the red and green points, they show up on the line, okay? Let's put this picture in our notes just to remind us. Okay, and move on. Okay, so now we're going to step up to a system. A system in math means more than one of something together, taken together. So if we have a system of two equations in two variables, that just means I've got two different equations, each with two variables, and the system includes both of them at the same time, okay? So now if I want to determine if the green ordered pair is a solution of the system, what do you suppose that means? Yes, it has to work for both equations in the system, okay? So there's a little bit stricter requirements for a solution of a system. For an ordered pair to be a solution of a system, it has to satisfy all of the equations in the system. You know, it has to make them all true. So we could check that. Well, we already know that the green point works for the purple line. Let's check it with the orange line. If I plug the ordered pair 3, 6 into the orange equation, I get 3 times 3 minus 2 times 6 equals negative 3. True or false? 9 minus 12 equals negative 3. Yeah, that's true, isn't it? Yep. So yeah, 3, 6 is an ordered pair of, or is a solution of the system because it's a solution of both lines in the system, okay? How about the red ordered pair? Well, we already know the red ordered pair is a solution of the purple equation. How about the other equation? Let's see, the orange equation. I'm going to get 3 times 6 minus 2 times 4 equals negative 3. True or false? False. So it is not, although it is a solution of the purple equation, it's not a solution of the orange equation. And so it is not a solution of the system because it didn't satisfy both. So what do you think what this would look like then if the green point is a solution of this system that includes two different lines and the red point is not? Describe what you're going to see when I show you a graph of the system and the points. Ah, okay, that must be the intersection, right? And the other one, you're right, is not on the intersection. Okay, so let's see what that looks like. Okay, here's what we get. Look at that. We get the purple line. Sure enough, it contains both points, but the orange line only contains the green point. The green point is the point of intersection, right? Okay, that tells us something important. Let's put this picture back in our notes. So you got it. That's one of the three types of ways that two lines in a system could interact. One possibility is that we get two different lines that must intersect at a single point. Wouldn't you agree that two different lines can only, at the most, intersect at one point? Okay, well, there it is. There are two different lines that intersect at a single point, so that linear system has one solution only. What are the other possibilities? Well, two different lines that never intersect. What kinds of lines are those? Parallel. That has no solutions. Okay. The other third possibility is we get two lines that are not different, two lines that are the same line, and they intersect everywhere that exists on either of the two lines because they're the same line. So it has an infinite number of solutions. So what's the terminology we can use to describe this stuff? Well, there's two words we use. We talk about dependence and consistency. A system is consistent if it has at least one solution. Okay. It's inconsistent if it has none. So what do you think? Thumbs up or down? Consistent? Thumbs up. It's got at least one solution. Consistent? No, that's inconsistent. No solutions. Consistent? Yes, because it has at least one solution. In fact, it has more than one, an infinite number. But it is consistent, though, because it has at least one. Okay, what about dependency? We say that the lines in a system or the equations in a system are independent if they're different, if they correspond to different lines. Okay, so whereas equations are dependent if they correspond to a line. So what do you think? Are these two lines independent or dependent? Are they different lines? Yeah, so they're independent. Are they different lines? Yeah, so they're independent. Dependent because they're the same lines. Okay, and so then if we wanted to categorize each of these systems using both of those two terms, here's what we would get. You told me those were the consistent systems, and this was the inconsistent system. And you guys told me that those were the two independent systems, and that was the one dependent system. And so aren't those the way that these are the ways that all three of those would stack up? This one is consistent independent, right? The middle one is inconsistent independent. And the third one is consistent dependent. And those are the only possible ways that we could build a linear system with two lines. Okay? Make sense? Okay, and again, this will be in your notes, so you can refer back to this. Okay, now let's get down to the nitty-gritty of solving systems. So I don't want to spend too much time on this slide right here because it's a lot of information and it's just too much to think of all at once. We'll just briefly take a look at it and look at kind of the overall process of solving a linear system using substitution. But then I want to go back and revisit these steps in the context of an actual problem so we can see how they apply when we actually solve a linear system. Okay. So what does this tell us here? Well, this is right out of your textbook. So step one, we're going to solve one of the equations for one of its variables. In other words, we could summarize that. We are just going to isolate a variable in one equation. Now we're only going to do this if it's easy to do. Otherwise, we're going to go to plan B and we're not going to use substitution. So what does that mean? It's easy to do. Well, it's easy to do if one of the variables has a coefficient of either 1 or -1. There's no other number in front of the variable other than 1 or -1. If you have a coefficient that's different than that, don't even bother. If you can't find a variable in your system with a coefficient of 1 or -1, move on to plan B. Don't bother with substitution. It's going to get too difficult. Okay, so that's step number one. We isolate a variable in one of the equations. Here's where I'm going to add my own little 2 cents on this that's outside of the textbook. Once you've done that, you've created your substitution equation, and you should put a box around it because you are coming back to that soon. Okay. Step two, once we've isolated the variable in one equation, we're going to substitute it into the other equation. Okay. And then once we do that, we're going to end up with an easier equation that we can solve for a variable to find out the actual value of one of our two variables. Once we do that, we immediately go right back to the boxed equation to find the other one. Okay, that's a lot of information. Let's see how it works. What about this system? Okay, this is a really easy one because both of the lines are already in slope-intercept form. Okay, so what are the variables that are already isolated? What variable is already isolated there? Y. And it's done twice in each equation. So take your pick. Well, I'm going to pick the bottom one to be my substitution equation because it's a little bit easier. Okay, so there's step one. It's already done for me. I isolate a variable in one of the equations. Step two, I'm going to substitute into the other equation. So there it is. Okay. Step two, we're going to plug the bottom y value into the top equation. So what's that give us? Well, what used to be a y has now been replaced by what? X minus 9. Exactly. Okay. And what used to be y that we replaced with x minus 9 is equal to -7x minus 1. Okay, so we made our substitution. Step three is solve that equation, which makes sense. What else are you going to do, right? You make the substitution and you solve for whatever variable you're left with. Notice that this accomplished a lot, though, because now instead of a complicated system with two equations and two variables, what we end up with is one easy equation with only one type of variable, which you guys are pros at solving. Been doing that all year, right? So what would I do to solve this equation? Oh, okay, so good. I'm gonna push the x's which way, left or right? Left. Perfect. Okay, so we're gonna push these guys over there by adding 7x to both sides. And if I'm pushing the variables to the left, I might as well push the numbers to the right. So I'm going to push the 9 over there by adding 9 to both sides. And what do we end up with? Okay, we end up with x plus 7x is 8x equals 8, which is easy to solve. What's x? 1. Okay. X equals 1. Okay, so now step 4. What do we do? Well, we solved for one variable. Step 4 is go back to the boxed equation and substitute. That's it. That's why we put a box around it, so it's easy to find. We take this thing and we're going to plug it in right there. Okay, and what's that give us then? That gives us y is equal to, instead of an x, we've got a 1 minus 9, which is what? -8. So then we end up with our solution. We would have to write in the form of an ordered pair because we solved for two variables. What goes here? -8 there? No, 1 has to because I have to do the x first, don't I? So 1 goes there and -8 goes there. How come? Well, because those are the values that we solve for. And then the last step is kind of a test step. That's where you would check this to see if your solution works in both equations. Using Desmos probably, right? On a test, you should definitely do that. On homework, I wouldn't do that. It's probably like you won't. Because if you miss the problem on a homework, you just pull up another one and try again. But on a test, you should always be checking that stuff, okay? Give me 1 to 5 on that. How are we doing? Okay. All right, then let's do this. I'm going to have you guys, try this on your own first. Go to the boards and try this. Do a little board work, and then we'll come back and work on it together. But I want everyone to think about it a little bit on the board first. So go to a board and give it a try. Okay, so again, let's you guys all did the heavy lifting for me here. You tell me what to do. So I've got this linear system. Which variable do I isolate? The y in the bottom equation, right? Okay, and that's easy to do. All I have to do to isolate the y in the bottom equation is just subtract 7x to the other side, and I immediately put a box around it. My substitution equation. Okay, now what? What do I do with that? Okay, good. I'm gonna, whatever I isolated a variable in one equation and now I substitute that into the other equation, right? It goes right in there for that y, okay? What does that give us? Okay, if we do that, then the top equation becomes 6x minus 5 times whatever I'm substituting in for y, so I make a space for that, equals negative 28. And what I substituted was this, negative 7x plus 22, right? Look what we did. Now that might look ugly at first, but it's not. That's good. Right now we've got a single equation with only x's in it, which is easy to deal with. So we clean it up by distributing. 6x, negative 5 times negative 7x is plus 35x. Negative 5 times 22 is negative 110. And now this is no big deal, right? We combine the like terms and get 41x. We add 110 to both sides, and we get 41x equals 82. Divide by 41, and what do we get? 2. Yeah. X equals 2. Okay, as soon as we solve for one variable, where do we immediately go? Back to the box. You betcha. We're going back to the other equation, and we've already solved that for y, so it makes it really easy for us to just plug and chug. I just plug that value of x in to find the corresponding value of y. So y is equal to negative 7 times 2 plus 22. So that's negative 14 plus 22. What is that? 8. Okay, so now we've got our ordered pair. We'll combine those into a single ordered pair. The ordered pair is 2, 8, and we're done. Give me thumbs. Okay, good, good, all right. Okay, so is that a good candidate for substitution? No, we're not going to use substitution there. How come? Because of the 4 and the negative 3 and the 5 and the 7. There are no variables that have 1 or negative 1 as a coefficient, right? If that was just like negative y instead of negative 3y, that'd be no big deal. I could solve for that easily, right? Solve for y. But it's negative 3y. And so, I mean, I'm stuck. All those variables have coefficients other than 1 or negative 1. So we just say no to substitution and we move on to plan B, which we'll talk about on Monday, okay? Good? All right, so then